Well, look how fun this page looks. I know how much you guys love words in math class. All right, so number 21, we have a boat costs $16,000 and decreases, that seems like an important word, in value by 7% per year. How much will the boat be worth after 13 years? All right, so what we have here is we are decreasing by a percent. This is an exponential decay. We have an equation or a formula for exponential decay. F of x equals a times 1 minus r raised to the x power. This a value is going to be our initial amount, starting amount, initial cost. That's our $16,000. The r is the rate of increase or decrease. In this case, decrease. By the way, if it's decrease, that's why we have a minus right here. If we had a situation where something was increasing, we would have a plus right there. So our rate is 7%. We do have to use the decimal version of that, so 0.07. And then in this example, this x is going to be our number of years, which is 13. So we're going to go ahead and fill those numbers in. F of x equals 16,000 times 1 minus 0.07 raised to the 13th power. Then what we do is we grab our calculator and we type it in exactly as we see it, being very careful with that decimal of 0.07. If we accidentally type in a 0.7, then we're looking at a 70% decrease, which is very different. All right, so when we type it in a calculator, we get back 6,228. We are talking about the price of a boat, so we need to have our answer in dollars and cents. We're going to include two numbers after the decimal, so it's going to be a 0.71, and then there's a 712. If there's a 2 after this 1 right here, if we have a 2, that's not going to round the 1 up, it's going to keep it as a 1. So we do want to make sure we have accurate rounding. So what's the cost of the boat going to be after 13 years? $6,228.71. All right, next example, number 22. A car costs $13,350 and decreases in value by 9% per year. How much will the car be worth after 6 years? So this is a very similar example. We're going to use this same formula up here because we are decreasing by a percent. This is exponential decay. Our starting amount is going to be 13,350. So I'm just going to start by plugging in 13,350. Again, if you jumped right to 22, maybe rewind to 21 just to hear me talk about this formula right here. All right, times 1 minus, our rate is 9% as a decimal of 0.09. And then we're going to raise that to the 6th power. That's where our number of years goes. We type that into our calculator, being very careful, especially with that 0.09. And we get back 7,581, and it's 0.054, so 0.05 is how we'll do our rounding. Throw a dollar sign on there. This is how much the car will be worth after 6 years. So you can see that it did go down in value as it said it would, and it went down 9% each year. All right, number 23. Suppose that the population of deer in a state is 15,100, and is growing 3% each year. Predict the population after 6 years. So this is going to be a similar formula or function as what we had up here, but this time we have something that's growing by a percent. That's our exponential growth model. So what that formula is f of x equals a times, instead of 1 minus, it's 1 plus our rate to the power of x. Our a value is still going to be our initial amount. In this case, we're talking population of deer, so it starts out at 15,100. So we can go ahead and plug that in, 15,100. And then we have 1 plus r, plus because it's a growth. And our r is this 3%, but as a decimal, 0.03. And then the power of x, that's going to be our number of years, which we can see right here. We want to know the population in 6 years. So then we grab our calculator, type it in exactly as we see it, including all the parentheses. If we're careful with how we type it in, we are setting ourselves up for success. All right, so we're getting, now, because these are deer, we're just going to round to the nearest deer. We won't have a decimal of a deer like, oh, 0.3 deer. So just keep that in mind as we're writing out our answers. So we have 18,030. It's 18,030.18. That's going to round down. So 18,030 deer. So after 6 years, the population will grow from this 15,000 amount to this 18,000 amount. All right, number 24. Suppose that the population of deer in the state is 12,900 and is growing 3% each year. Predict the population after 3 years. All right, so we just did one very similar to this, so we're just kind of practicing our skills. F of x equals, just going to follow our growth formula up here because we are growing at 3%. That's exponential growth. Our A value is our starting amount, so we're talking deer. Starting population is 12,900. Inside the parentheses will be 1 plus because it's a growth, and then 3% as a decimal is 0.03. We're going to raise that to the power of 3 because we want to know how many deer we'll have after 3 years. So then, grab your calculator, type it in very carefully, and when we do that, we get 14,000. I'm going to run this to the nearest deer, so 096. This will be the population of the deer in 3 years. That's what we are predicting. All right, number 25. Find the balance of an account after 10 years with a principal of $800, earning 4% interest, compounding semi-annually. All right, so compounded is a key word. This is a finance problem. This has its own formula, and it has the formula that has the n's in it. So this formula is A equals, so A is going to be the total amount after so many years. P is our principal times 1 plus, we're going to have a little fraction, R over N, close your parentheses, raised to the NT power. All right, so this P right here is our principal. The principal in finance is the starting amount, the amount we're investing, the amount we're depositing. In this case, that's going to be $800. When we invest money, it's going to grow, which is why it's a 1 plus versus a 1 minus right here. Our rate is going to be the percent as a decimal. So 4% as a decimal is 0.04. This N is our number of compounds per year. When it says compounding semi-annually, so annually would be once a year, semi-annually is twice a year. We can see we have our N up here and our exponent again. We're going to use that same 2 there. And then T is our time. We want to know how much money we have after however many years. So we look for that time and we can see it's 10 years. All right, so let's go ahead and rewrite this with all those numbers plugged in. Our principal is 800 times 1 plus our rate, 4% as a decimal, 0.04, divided by n, number of compounds per year. Now, remember a compound, I didn't explain that at the start of the problem. A compound is how many times in a year you calculate interest on your account. So you can compound a variety number of times in a year. But that's what it means. You're just saying, all right, let's stop. How much money is in the account? Let's calculate interest on it and then add that interest into the account. Then time goes on. Oh, we have to compound again. We stop. We calculate the interest on the account, which now has a little bit more money in it because we added in interest at the last compound. So that's what compounding is. Now our exponent is n times 2, or n times t. So our n is 2 and our t is 10. All right, so we're going to type that into our calculator very carefully. You can use the little fraction button on the calculator, which is handy. All right, so this is a money problem. So dollars and cents, we're going to round to 2 decimal places. The amount of money we have after 10 years is $1,188.76. We have to round that 75 up to a 76 cents. All right, number 26. Find the balance of an account after 12 years with a principal of $1,000 earning 6% interest compounded monthly. So there's the key word. When we see compounding in a problem, that tells us we're going to use this formula up here. So if you're jumping into number 26, maybe rewind back to 25 just to hear me go through what all this stands for. But since we did just talk about it, we can jump right to plugging in our values. So A equals, P is our principal. Principal is our initial deposit or investment. That's the $1,000 times 1 plus our R is the interest rate as a decimal. So 6% as a decimal is 0.06. Divided by N is the number of compounds per year. So if we're compounding monthly, N is equal to 12. We're going to raise that to the N times T power. So we have that N again. So there's our 12 times our T, which is number of years. And we can see we're looking at 12 years. Then we very carefully type that into our calculator. Be careful with that 0.06. Don't accidentally type in 0.6. That would be 60% versus 6%, which is very different. We're going to get an answer in dollars and cents. So we have $2,050. I need two numbers after the decimal. So I have a 0.750, so that will stay at 0.75. So $2,050.75. All right, we made it to number 27. Write the recursive and explicit formula for the geometric sequence 4, 8, 16, ... So a geometric sequence, this is a sequence of numbers that increase with a constant ratio. And how you get from one number to the next and to the next is with multiplication. So we want to first figure out what that constant ratio is. Sometimes you can look at a sequence of numbers and just kind of tell, like to get from 4 to 8, 8 to 16, oh, we're multiplying by 2. But we also can set up ratios and see if we have a common one and what that is. To set up the ratios, we're going to jump to our second number 8, and we're going to divide it by the term before. Now I'm going to jump to the third number 16 and divide it by the term before. 8 divided by 4 is 2. 16 divided by 8 is 2. So that's our common ratio of 2. In order to write a geometric sequence, we need to know our common ratio. And we also need to know our first term, a with a subscript of 1, a sub 1, equals, and we can see right here, 4 is our first term. All right, we can write any sequence with those two pieces of information. That's all we need is the first term and the constant ratio. So let me remind you what a recursive formula looks like. Recursive formula is a sub n equals our common ratio, 2, times, in parentheses, a subscript n minus 1. And then we have to identify with a1 equal, and then fill in what the first term is. So n is the term number. So if I needed like the 10th term, I would write a sub 10. So that's what that number stands for. What this is telling us to do is it's telling us to take this notation right here, a sub n minus 1, that's our previous term. So they're saying take your previous term and multiply it by 2. That's how you get the next term. Then do that again. Take your previous term, multiply it by 2. Take your previous term, multiply by 2. That's how you can build a geometric sequence with a recursive formula. The thing though is you do have to tell people where to start. If you just say, hey everyone, take the previous term, multiply by 2, you'll say, well, starting with what number? And that's why we identified the first term. All right, so let's go ahead and write out our recursive formula for this sequence. We're going to follow this structure. So our recursive formula is going to be a sub n equals, oh, look at this. I am going to change this to, whoa. I filled in the 2 by accident too soon. That should be an r. It's r times. So our common ratio gets multiplied by the previous term. Now let's go ahead and fill in. We know that our common ratio is 2 times a sub n minus 1. So there's our rule, and then we just need to tell people, hey guys, start with a1 equal to 4. This is the information we identified over there. So here's our recursive formula. Limitations to a recursive formula. If I needed the 50th term of this sequence, I can only find it by using the 49th term, by using the previous term. I can only get the 49th term by using the 48th term. So in a recursive formula, you can't jump ahead to find a specific term. You have to build from the beginning. An explicit formula is a little bit different. So our formula for explicit is a sub n equals a1 times our common ratio raised to the n minus 1 power. So if you know your first term and your common ratio, we can just write this out. We have both of those pieces of information. So our explicit formula, an equals a1 is 4 times our common ratio is 2 raised to the n minus 1 power. That's our explicit formula. So an explicit formula, what's nice about these is you can jump to any term you need. You do not need to build from the beginning and work off of the previous term. If I want to know the 100th term, I just plug in a 100 for this n right here. 4 times 2 to the 100 minus 1 power. I do that math. I've got my 100th term. If I want the 1 millionth term, I just plug in a 1 million for the n. So this is a little bit, well, this is a lot easier to use, more practical in my mind, but it's good to know that we can also write a sequence in a recursive style as well.